welcoming the participants. Nau mai, haere mai. A welcome from the Nelson Tasman Climate Forum, which has the pleasure of our guest, Jim Salinger, tonight. But I'll begin with a short karakia. Hui hui mai tātou I tēnei rā, kia tipu tahi, kia ako tahi, tātou, tātou katoa. We come together today to share, grow, and learn together. So, let me introduce you to Jim Salinger, who has been named as the Kiwibank New Zealander of the Year, Te Pou Whakarai o Aotearoa. Dr. Salinger is recognized as one of the first scientists to address global warming and has dedicated almost 50 years to advancing climate science. Born in Dunedin in 1947, he completed a Bachelor of Science from the University of Otago in 1971, a doctorate from Victoria University in Wellington in 1981, and a master's degree in environmental law from the University of Auckland in 1999. He's currently an adjunct research fellow with the School of Geography, Environmental and Earth Sciences at Victoria University. Jim Salinger is an influential communicator on climate change and has addressed audiences nationwide. He's a companion of the Royal Society of New Zealand, an author, and has published extensively in academic journals. He was the lead author for the Intergovernmental Panel on Climate Change in 2007, the year in which the IPCC was collectively awarded a Nobel Peace Prize. Among Jim's other awards are the New Zealand Science and Technology Medal in 1994 for groundbreaking research on Southern Hemisphere climate change, and the 2018 World Meteorological Organization Award, and the 2019 Jubilee Medal in recognition of his lifetime achievements in climate and agricultural science. I will also insert here that Jim is a member of Wise Response, a very valued climate organization in New Zealand. I want to mention a book that Jim Salinger edited, published in 2013. It's called Living in a Warmer World: How a Changing Climate Will Affect Our Lives. And the particular reason I want to mention it is I want to encourage you to read it. It's an excellent foundation for thinking about adaptation, because Jim collected experts in the various dimensions in which we need to think about adaptation, such as nature and insects, water, sea level, grains, livestock and fish, health, heat waves, infectious diseases. So a little plug for a book that's been around for a while, but absolutely worth reading. Now, in our audience, we have many folk who are dedicated to action on climate change, and it can be, I know, a challenge to simultaneously do the things that so urgently need doing and also keep up with the science of climate change. And that in particular is why we've invited Jim to speak to us tonight. So thank you, Jim. And in a moment, over to you. Just before I pass over to you, let me tell the now 63 participants that if you look at the lower part of your screen, towards the right, you'll see an icon for Q&A. And that's where you put your questions to Jim. You can enter them at any time during the talk or after. And you can also vote. If someone else has put the question that was on your mind, give it a vote, and we will choose from the questions that are popular. I'll be helped in that part of our evening by Chris Wheatley, and introduce Chris shortly. You know that this is being recorded, and I'll tell you details about how you can access that at the end. But for now, over to Jim.
Thank you, Joanna, and I'm delighted to be here on we'll call it a cool winter night. I live in Queenstown, and I think we're in the full throes of midwinter, but it's always bright down here. Plenty of sunshine, can get cool at night, but otherwise okay. So what I want to look at tonight is firstly just a primer on the greenhouse effect. I'm sure a lot of you, it's not new to you, but it's always useful to refresh our minds about it. Then I want to look at trends in greenhouse gases, because this is very critical to what's going to happen in the future. And let's update on temperature trends, because one hears all sorts of things, but it's nice to have the most updated information. Then I want to look at where are we today, because that's very important for how we move ahead. Then on top of this, we'll look at future trends, and I think very importantly, climate action. But I think when you look at climate action, you don't want to think about doing it all at once. We take small steps to get to our goals. So the greenhouse effect. Well, this slide on the left-hand side where I've got my arrow is the natural greenhouse effect. And if we look at that, you get solar radiation from the sun. Now that's shortwave radiation, and the atmosphere is naturally mainly transparent to that, and that shortwave radiation goes to heat up the surface of the planet, be it ocean or land. And then, because the Earth is a cooler temperature than the sun, it re-radiates this energy as long-wave radiation. And this is where the greenhouse gases come in. There are carbon dioxide, methane, nitrous oxide, naturally occurring greenhouse gases. And what they do is they're transparent to the solar radiation, but they're opaque to the radiation from the planet. If we didn't have these greenhouse gases, we'd be like the moon. We'd get very high temperatures during the day at the surface and very frigid at night. But what these greenhouse gases do is they delay the transmission of the heat out to space, and the resulting temperature, well, of planet Earth, I think the mean temperature is somewhere around 14 degrees. If we didn't have them, we'd be a lot cooler. Now, well, what happens when you add more greenhouse gases to the atmosphere? What you do is you still get the solar radiation from the sun, but you get the heat that is re-emitted trapped by more greenhouse gases, and then this is re-radiated back to the planet. So it's like you, and on a cold night, what you do is you putting another blanket or two on your bed. The air above your bed gets colder, but you get warmer. So that's all it is. It is less heat escapes to space, as compared on the left-hand side, more heat escapes to space. Now, looking at the next slide, what's very interesting is if we look at greenhouse gas trends up to, shall we say, the 19th century and going back 800,000 years, and we can get what the carbon dioxide concentration was from Antarctic ice cores. And what they do is they drill down into the Antarctic and they go down and down and down in the layers. And in these layers are bubbles of air, and they can date those bubbles of air because they've got carbon in them, and so you can date that through that, and they can measure carbon dioxide concentration in these bubbles. And what you find is you have times when there's more carbon dioxide and times when there's less carbon dioxide. In terms of parts per million, it ranges from 180 to 280 parts per million. And similarly with methane, they find it going up and down and up and down. I will deal with the recent rises shortly, but I think the point is there's been this cycles, and if we look at the next slide, what we see is here we've got carbon dioxide. Again, on an expanded scale, you can see the carbon dioxide ranges between 280 parts per million and about 180 parts per million. In the red are temperatures, and they can measure this from these bubbles in something called the oxygen isotope ratios. And what you see is the variation between temperature and carbon dioxide concentration are very much synchronous. So you have these periods where temperatures, there's the zero. So effectively, these are glacial, interglacial cycles. And so they're very strongly related. We talk about glacial cycles as when you have the huge ice caps of the world covering the Laurentide area in North America and Fennoscandinavia in Europe. You have these ice sheets. We call these ice ages. Then we have interglacials, which really means you've still got glaciation in bits of Greenland and in Antarctica. So it's between major glaciations when you have expanded ice sheets on the northern hemisphere. So it's not non-glacials. The interglacial means between these freezes. Now, I think what you need to look at in this diagram is this here. So this shows you carbon dioxide shooting off the scale. So what this is showing today, how the two are out of balance because of human activities. And you can see that it was between 180 and 280 parts per million until very recently. And this is just showing you since the last glacial maximum about 20,000 years ago, and the ice core records, you can see that carbon dioxide was very much synchronous with what's happening with temperatures. And you got the recovery since the last glacial maximum into this interglacial. So the theme is these are very linked. So let's have a look at what's happened recently. Well, with the Industrial Revolution, of course, you had suddenly the use of fossil fuels. And really, since about 1850, you've had a huge growth in the emissions of fossil fuels until we're somewhere near, in terms of carbon dioxide, 420 parts per million. So we've increased the amount of carbon dioxide in the atmosphere very dramatically. This shows you the same graph for methane. It's probably not that clear, but the point is we were somewhere around 700 parts per billion. We're now over about 1,800 parts per million of methane in the atmosphere. Methane is another of these greenhouse gases. So we'll move to the next slide. This shows you measurements by NIWA of carbon dioxide at Bering Head. And what you can see there is there's an annual cycle. If I had pulled it out, but as of 2023, we were up to about 417 parts per million. So a dramatic increase, and this would start back at, if we'd been measuring it at Bering Head in 1850, which we weren't, be around 280 parts per million. Similarly, we see the same thing happening in methane, and here you can see very clearly the annual cycles, and we're now above 1850 parts per billion and rising rapidly. So what we see is a dramatic increase in greenhouse gases in the atmosphere. So it's no wonder we see increases. And if I was to plot this against temperature, so on this side you've got carbon dioxide concentration. This is a Northern Hemisphere value from Moana Loa, top of Hawaii, as against global temperatures. And this is a 20th century average. And basically, global temperatures have increased in the order of, shall we say, 1.2 degrees centigrade. So there's a good link, but obviously the temperature of the planet has a bit of a lag with carbon dioxide because the system takes a while. As you see, there was little reaction, and now since about 1980, it's been quite dramatic. When I did my postdoc at University of East Anglia, around 1980, we were seeing the rise in increase in temperature. Then we predicted that by decade 2000, it would be clear to everybody, and some of us also foreshadowed we'd see dramatic climate extremes emerging in the 2020s. So moving on, I want to now deal with New Zealand, and luckily we had very good observing standards in New Zealand. When I refer to New Zealand temperature trends, I like to think of not the land area, but shall we say the land plus the exclusive economic zone, because our oceanic area is 15 times larger than the land area. So in a sense, I call it the land area. You can see here that there's a lot of continental shelf areas. To the south, the Campbell Plateau, Chatham Rise, and then there's the Challenger Plateau that heads up to Norfolk Island. And because of this, we have a very large exclusive economic zone. So I like to look at temperatures both for the land, but for our sea area and combined because we're very much the centre of the oceanic hemisphere. We're very lucky in New Zealand that when Sir James Hector came out, he was a very dour Scotsman. He was, in a sense, the chief scientist, and he set up all sorts of things, but he then set up a very good observing system where he specified that temperatures had to be precision thermometers. So you've got their sheath thermometers and in louvered screens. These are called Stevenson screens, and copper rain gauges. So he was very insistent on rigorous homogeneity and very good observing patterns. And that served us well because in England, they hadn't decided what their standards were, and they had all sorts of measuring systems and funny ways of exposing thermometers. And in Australia, each Australian state did its own thing. So we have a very good climate record. There's not a lot of stations were set up, but what we've got is very good. And there were also methods of measuring sea surface temperatures. And there's lots of records, and people have worked on databases in the UK and everything, and ships at sea would take sea surface temperature records. And prior to World War II, they used to have buckets, which they'd throw out into the ocean, and then they would measure the temperature wherever the ship was. And so they had wooden buckets. They also had canvas buckets, and they also had insulated buckets. So as in the early days, most of the ships plied the oceans, but they collected all these records, and in Britain they archived them. And because of this, we have our sea surface temperature that go back to the 1860s. Obviously, after World War II, they changed the ways of measuring them to engine intake. So there had to be adjustments made because of the way these sea surface temperature observations were made. But because of that, we've got records of what happened in the surrounding oceans around New Zealand. Now, this just shows you, this is degrees Fahrenheit, don't worry about that too much. 1.8 degrees Fahrenheit is 1 degree centigrade. Anyway, this shows you a diagram of human natural influences on global climate. And what it shows you is the observed changes in global climate back to 1880. So this is this black line here. And as you can see, it goes up and down, and then from about 1980, clearly increases. Now, through climate modelling, they've been able to disentangle what is natural. In natural drivers, you have volcanic eruptions. There's Krakatoa, Pelée. You can see how the temperatures are very severely depressed. Then we had Mount Agung in Indonesia. Then we had El Chichong in South America. And then some of you will remember 1991 Pinatubo. So when you have a volcanic eruption, what happens? It puts a dust veil of sulfur dioxide into the upper atmosphere, and this hydrolyzes to a sulfuric acid mist, and you get a few seasons of depressed temperature because the sulfuric acid mist basically reflects sunlight back to space, and you get some very lovely sunsets. And those of you who can remember very colourful in the sky at night. That's if you can remember back to 1991, those of you who are older. So this is a natural variation. There are other things such as solar and orbital, but these are on much longer timescales. If you then say, okay, let's look at the human drivers of climate. So the blue is what would happen if you just have the natural drivers. The next type of driver is changes in obviously greenhouse gases. And what the models have done here, and this is the red line, is if you add increasing greenhouse gases to the atmosphere, as I said, it's about the signal sort of separates out about 1980, you'd expect the climate system to warm, and the warming signal really separates after 1980. Quite apparent once you get to 2000, and there it goes. And if you combine these, remembering you can see the effect of the volcanic eruptions, you go back, there's Krakatoa, there's Pele, which is in the Caribbean, Agung, El Chichong, and Pinatubo. So they have a few seasons cooling, but then it goes back to what you'd expect it to be. So that's the modelled, and this is what we've observed is the black line. And you can see Pinatubo in there, El Chichong and Agung, they're there, and particularly Pele in about 1902. So that's what they've been able to show with modelling. Now, what's interesting is to look at what's happened in New Zealand. And what I've done here is pulled out what have I done? Ah, yes, let's just put things down there. I've pulled out the land record, and these are the climate stations. We can go back to about 1870 here, and we have Krakatoa. This was actually Mount Tarawera. It doesn't come out in the global record, but it comes out in ours. There's Pele, and then we have Agung, El Chichong, and Pinatubo really stands out. So that's if we have the land. But because we're surrounded by ocean, we need to look at our ocean temperatures as well. And they're largely in concert. Again, Pinatubo stands out, as does Agung and El Chichong. Agung. Then you go back to Krakatoa and Tarawera. But Pele is certainly the one that really pushed him down. So if you add the land and the sea together, and I've smoothed it here, you get this trend. And basically, we see for New Zealand an increase of 1.3 degrees centigrade. The warmest years have been 2022 and 2023. And this is just a smoothing, so you can see more the trend. Now, this is really just to show you what we'd expect from the New Zealand curve with the greenhouse effect. Basically, this red is what you'd expect of the greenhouse effect on New Zealand climate in terms of global warming. This is the actual land and sea record. It wobbles around and then it shoots up dramatically recently. And this is the land here. And you can see these basically are sort of error bars. So and you can see the arrows of when major volcanic eruptions occurred. Krakatoa, Tarawera, Mount Pelée, Mount Agung, El Chichong, and of course Pinatubo. Pinatubo had a major effect globally. So where are we today? Well, this is very important because this shows you the temperature anomaly compared with 1991 to 2020 of June 2024 globally. And you can see, you heard of all the heat waves that have been going on. Well, they're real. And you can see they've very much been very much above average temperatures, 2 to 3 degrees right throughout Eastern Europe and throughout Africa and the Sahara and to equatorial Africa and North America, and particularly in Labrador and also in China. And if you watch BBC weather at times, they're saying how much above average. And even in South America, June was a warm month here as well. So that's up to the present. What's more spectacular is if you look at the last 80 years, this is 2023, which globally was by far the warmest year on record. So that ends up there. So it was very warm, particularly in the second half of the year. It was because we went into an El Nino. There's a specific reason for that. You can see how much it's been above average for the first, this is globally, for up to the end of June. It's been an incredibly warm year, and figures have it we've reached in that 12-month period plus 1.5 degrees centigrade above average. I thought I'd pull out the Nelson temperature record since I've shown you the New Zealand one. This is the Nelson one, and you can see temperatures 2022 and 23 for Nelson were the warmest on record. The record there goes back to 1908, and you can see it's about 1.4 degrees centigrade compared with what it was back just in the first decade of the 20th century. And there's a dotted line here which just shows you a smoothing, so you can pick out trends. Pinatubo's there. It's always pretty obvious. And you have Agung, and then in this period here, there were a few cold years. What's interesting, it doesn't matter where you look in New Zealand. This is the number of, blue is the number of days are below zero. In other words, frost days in a year. Now, what you can see with this, there used to be about 20 to 22 days a year when temperatures were zero or, well, below zero. Now we're down to somewhere around 13 days, so it's dramatically reduced. This statistic is not quite as dramatic as the loss of frosts. It's the days above 25, but you can see that it has been increasing. In other areas, this is much steeper. So in other words, we call these summer days. Well, 25 isn't hugely warm, but that's what's been happening. Now, if we look at what's happened now, this is what this relates to. Sorry, ignore that one. This is showing you New Zealand climate over the last 80 years or 84 years. So this goes back to 1940. You can see how warm 2022 and 2023 have been. They were the New Zealand's warmest and second warmest year on record. And you can see black is up there. This is only the first 3 months of 2024. We were in an El Nino this year, which is not as warm as when we have La Nina in the Southern Oscillation occurring. So you can see the band of New Zealand temperature. That's an incredibly warm month. That's January 2018. You can see the range for New Zealand temperatures, and it's fairly tight. It's 15, so 5-degree band between the hottest and coldest in any one month. Winter is 4-degree band, but we don't have a hugely variable climate, but you can see that there is quite a bit of variability, but in the last 84 years between the warmest and coldest. And so that's a similar graphic in a sense to that, but except it's done on a monthly basis rather than a daily basis, but it shows the same thing. So what's going to happen, and this is the critical question, with greenhouse gas concentrations. This is parts per million, and of course we're somewhere around 420 at the moment. And working out temperature projections, the scenarios use greenhouse gas concentrations and carbon dioxide equivalents. So this is the highest emissions pathways. So they're saying, okay, if things go unimpeded, we end up with, say, 300, about 4 times what was the 1850 concentrations. If you take a higher emissions pathway, not the highest, so this represents a doubling. This is not a doubling, but more, and the low emissions pathway, one ends up not too much above today's levels. And so people have worked out what happens to the climate with various emissions pathways. What's very important, though, is what our climate policies are. And this will then move on to the last section of my talk. So we're looking at I'll just go back one, where we are today. So future trends, this really depends on human behavior over the next 3 decades. And it's quite critical. If you didn't have any climate policies, this would be expected, this purpley pink area, expected emissions in the baseline scenario of countries had not implemented climate reduction policies. So according to these scenarios, you look at annual global greenhouse gas emissions and more gigatons are being emitted, and you'd end up with temperatures by the end of the century about 4 to 5 degrees centigrade above pre-industrial. This is how they're measured on. Next group is emissions with current climate policies in place, resulting in a warming of 2.5 to 3 degrees by 2100. So this is this band here. And these are based on, they're not based on pledges. The next here is pledges and targets. Missions of all countries delivered on reduction pledges, resulting in a warming of 2 degrees by 2100. So in other words, they're saying if the pledges that countries have made work out, this would be, we would end up with about 2 degrees warming. Now, this shows you New Zealand's historical and projected greenhouse gas emissions. So as this was updated last year, and so you've got the gross range and you've got the targeted accounting range, and these are target accounting and gross and targeted accounting. So the hope is to reduce emissions by 2050, and basically they're saying, well, we need to, in terms of gross emissions, have them down, but this then allows emissions, obviously with carbon offsets. So that's net, and the idea of this is that it would be less than half of where we are today, which seems quite a tall order at this stage. There's a site called Carbon Tracker, which actually assesses based on modelled domestic pathways, and this NDC is National Determined Contribution, and in policies in action, New Zealand's overall rating is highly insufficient. And so we've been assessed as highly insufficient and almost sufficient with this target for a less than 2 degree world. So we're not judged very well. As you see, we seem to be in the nationally determined contribution in the insufficient area, so we need to do better. This shows you land use and forests, so that's carbon offsets. Land use and forests have historically been in emissions, and there's the land use and the forests up to date. This was a November 2022 update, so it's not looking good for us. So I think in the last bit, I want to talk about what we can do. And there's a number of things we can do, and they don't depend on government policy. It's our actual individual behaviour. But again, I can't tell people what to do. They have to decide themselves what they want to do. So this here is, and obviously this is being recorded and will be available, is a very useful carbon footprint calculator where you can assess your own carbon footprint. It's a bit like if you want to reduce your electricity consumption, you need to know what electricity you're using and where it's going. And this website, and this will be available in my presentation, will enable people to decide what they can do themselves. I'm not going to tell people what to do. It's best they do it themselves. So you have various, you can look at what you do in your house. This is flying. This is car, motorbike, bus and rail, secondary, and then you get the overall results. Just to show you, this shows you the secondary carbon footprint calculator. And this is food and drinks. So this is what you might be looking at in terms of your consumption in a year. And it comes out with, as you can see here, the amount of metric tons of carbon dioxide you might be producing as a result of your, shall we say, buying computers and IT systems, clothes, pharmaceuticals, etc., etc. I just sort of assume some things for myself, and it's very useful in terms of knowing what your carbon footprint is. And okay, so the biggest one for me was I obviously fly too much, and that was no surprise. But I have an EV, so that's going to be low. Don't have a motorbike and do use a bit of public transport. And so it comes out with your footprint. And so this is a New Zealand country average. This is a world average. And I'm a bit better than the New Zealand country average, but obviously when you add in all the countries in the world, I'm worse than obviously less developed countries. So I know that I need to cut down on flying places, things like that. And doing webinars like this is one way of saving carbon. But it's a very useful tool to use to give you a guide on what you're able to do. So really, you can see I can cut down a lot by stopping flying, and that takes about 4 out of the 5.5. So that shows you this where I can improve what I'm doing. And then you can go to a page and they even give you suggestions. And obviously this is UK based because the average family of 4 creates 10 tons of carbon dioxide emissions each year. So they suggest cost saving actions, this in terms of carbon footprints: hang out the washing instead of tumble drying, turn down your heating in the house, Only fill the kettle with the amount of water you need to boil. Spend less time in the shower. Turn electrical equipment off when not in use. So they've identified this will save you basically 437 kilograms of carbon dioxide of these 10 tons, saving you money. But I think the point is clearly in UK they have much more fossil fuels in their electricity production. So what one needs to think about, and it is important, is I like the Gandhi principles. Whatever you will do will be insignificant, but it is very important that you do it. In other words, lots of collective action, when you add it all up, makes a huge difference. And as I said, a lot of these actions do not depend on current government policy. And my comment is that our government is doing a lot, so really we need to do more in this period. Well, this is basically lobbying government, but I'm sure that's going on. So agriculture is quite sensitive, but eat less meat and dairy is reasonable in the terms that once you're more on a vegetarian diet, you're using, shall we say, biological energy much better, because basically animals feed on plants, so you're at a lower, what's called a trophic level, in other words, a feeding level. Therefore, you're taking in plant protein, carbohydrates, fats, and you're not going through the intermediary where the animal consumes these plants. And in doing so, a lot of energy is lost. So the food energy is going straight into you without it being going through another process. And that's the reasoning about eating less meat and dairy. The other thing is, ruminant agriculture, of course, has its own emissions. Cut back on flying. Well, that's what I need to do because that's quite energy intensive. Yes, I have an EV, but again, so EVs don't rely on fossil fuels. So these, again, are useful. Well, we have a huge number of roofs in New Zealand. A friend of mine said if he's an electrical engineer, he said if he had his time again, he would have rented a whole lot of factory roofs in South Auckland and put solar panels all over them so that he could generate electricity. And that was a good thought, because you think of the area that's just taken up with roofs, and particularly in industrial areas. Increasing walking and cycling, and that's good for all of us because it means we are much more healthier population, and exercise, and that's also good. So it's called active transport. It's unfortunate that the John Key cycle trails funding has been terminated, because they've been very popular in a lot of areas in New Zealand, and a lot of people, and it's people who are more advanced in their years as well, can do cycling and walking, and it gets them out of cars and is much more healthy. Obviously, reduce your energy use in bills. Green spaces, this is very important, and obviously conservation is a useful activity. This is really responsible investment that deals with, and the last one is cut consumption and waste. Now, I'm sure that lots of you are doing quite a bit of this, but as I said, there's a lot we can do despite whatever the current or future governments are doing. And so it is in our hands, and we need to take action. And I'll just go back. So these are our choices. Now I'll sum up at this point and say, I've talked about the natural greenhouse effect of trace gases in the air, which keep warmer than the earth, warmer than it would otherwise be. Otherwise, we'd freeze at night and we'd be very hot during the day. We've been able to trace since the mid-19th century the increase in greenhouse gases way above the glacial interglacial cycles, and methane itself has doubled. There's no doubt that the enhanced greenhouse effect has warmed our climate since 1850, and it's continuing to warm, and we're now in the era of getting lots of climate extremes. The other day, for example, Death Valley reached 54 degrees centigrade, which is not a very survivable temperature. And both global and New Zealand temperatures have increased by 1.2 degrees centigrade or more, with last year being the warmest on record, both locally and globally. And most of us who work in climate view current policies. We will not prevent the climate warming by around 2 degrees or a bit more, unfortunately. We're on a warming trajectory unless we get very active. And my appeal to everybody is to take climate action. A good way is to work out what our carbon footprint is. There is the website to go to, and it's a very interesting exercise to do, because then it points to you where your biggest carbon footprint is, and then some people run it as an exercise and know your number, and that gives us a guide as where we can reduce our carbon emissions. And it is very important actions we can take ourselves, whether it's conserving energy, using renewable energy, solar, wind and hydro, and choosing active transport, etc. Not for me to tell you what to do. It is useful for everybody to identify what they think they can do and come up with it themselves. And a lot of these actions are independent of government policy, and we need to get independent of that, as shown by some of the things that are going on. Anyway, thank you, and we can do it, but remember, it's important to just start on the journey and do it all in small steps. If you think, oh, right, this is what we've got to do, I think it's best to take small steps at a time to arrive at on the journey towards the destination. Thank you. And back to...
Thank you very much, Jim. for a very clear elucidation of what we're dealing with. May I introduce Chris Wheatley? Is it possible for Chris's image to join us in this panel? Chris and I are planning. Excellent. Chris Wheatley is the Deputy Chair of Nelson Tasman Climate Forum. Okay, so let's dive into the questions, and Chris and I will alternate selecting questions. I'll start with an early question that was posted, or two questions posted, having to do with the impact of air pollution and particulate matter on climate change. Could you say something about that, Jim? And also the impact of lowering air pollution and particulate matter.
Right. Okay. This goes back to the London smogs in the 1950s. Air pollution and particulate particles have always been an issue, and certainly with the London smogs, because they caused a lot of death and fogs. And when you get that, and we have examples of that in the southeastern US, and that appears to have reflected some light back to space so that there was less warming. If you get rid of the particulates, then air pollution, then the atmosphere is clearer and the surface warms a bit more. That would be my quick answer to that. But there's also good health reasons not to have air pollution, because people get lots of lung complaints, and this is what was happening in the 1950s.
Thank you, Jim. So as we clear the air pollution, we may be subjected to some degree of increased warming have a phase.
Yes.
Okay. Chris, over to you.
Yeah. Okay. I'll choose a question about have changes in policy settings by the current government been modelled relative to the targets set? Okay, so that's a big question.
Yes.
So,
that's the question, is it?
Yeah, that's the question. Yeah.
Well, I think it's quite clear that agriculture's the policy settings there. We see, in fact, that agriculture doesn't have to do anything until at least 2030. Now, our methane emissions and in terms of agriculture policies have basically, they're half our emissions. And this will probably create problems, because I believe Nestle is putting pressure on Fonterra to clean up its act. Otherwise, Nestle, which is a huge consumer of Fonterra's products, decided they may not take them. So this might be a bit of, shall we say, consumer resistance in our biggest market in terms of Nestle and other things. So I believe Fonterra is going to perhaps put pressure on the agricultural sector to reduce emissions. That's an interesting one. The other policy setting is, if you look at the land transport policy, and remember that's a huge sector as well, you'll notice the word climate only comes up once. So the revised policy setting does not seem to allow for land transport emissions due to vehicles. So I think it'd be fair to say that we're on a go slow in terms of our emissions reductions target. And it looks like what's going to happen is they're going to put all their money on fixing up natural disasters. Well, I won't call them natural disasters. Climate disasters as they occur. Well, this is not particularly proactive.
So more focus on the dealing with the consequences of climate change and not so much on the causes.
Yeah.
I also noticed, sort of as a supplementary thing, from one of your graphs, the nationally determined contributions wouldn't still keep us at 1.5 degrees, right? It's still
no
up to 2.
Well,
so that's
Well, we're almost there anyway. So I don't think the globe will keep below 1.5. We've got to have a chance at keeping below 2. So I think most of my colleagues would agree that 1.5 is gone. We're going to be a lot warmer. And I hope the younger generation will get angry about this.
Joanna, back to you.
Yeah,
they have every right to.
They do. It's really a bad prospect. A question from Fred Overmars, which also occurred to me as you were talking, Jim. The graphs of hundreds of thousands of years of history of variations in methane concentration. What drives the seasonal variation in methane concentrations?
And carbon dioxide the same. It's driven by the northern hemisphere because you've got large land area there, which supports plants. So obviously the plants through photosynthesis, and when the northern hemisphere is in winter, there's less photosynthesis, and I might get it mixed around. When the northern hemisphere is active, it's combining carbon dioxide and water to form sugars. And so this would absorb more carbon dioxide. And in the winter, there's less. So that's seasonal, and similarly with methane. So that's driven by the northern hemisphere. You have to think of the southern hemisphere as mainly an oceanic hemisphere. 80% is ocean, whereas the northern hemisphere has the larger land masses. So that gives you the seasonal variation.
So is the CH4 seasonal variation due to faster rotting of organic material?
Yes, it's everything when on the land areas goes, it varies between winter and summer, but yes, you'd be right there.
Right. Over to you, Chris.
Okay, now a question from Lindsay Wood. She's interested in the role water vapor might play as a greenhouse gas, especially as air temperatures rise and the saturation capacity of the air increases disproportionately with that. Could you comment on where the research and scientific thinking is on that water vapor?
Yes, well, water vapor is a greenhouse gas and no one disputes it. Basically, where the thinking on that is it's sort of an enhancer of the greenhouse effect, but because it's so variable, unlike the trace gases, it depends on where you are on the planet. But it's recognized that what you're having is it's a feedback loop effectively. So the more water vapor, the warmer it gets because it is a greenhouse gas. But there are lots of areas where there's not a lot of water vapor as well. So it's not like you're increasing the total water vapor in the atmosphere. It varies.
Thanks. Yeah, got that. Okay.
Okay. Rachel Bolstad wants to ask you if you have any suggestions for action that's about systemic change.
Systemic change being...
Well, I think she's probably distinguishing it from individual actions that we can immediately have control over, to trying to change
behavior.
our system in some way, either our transport system or our food system at a higher level than individual.
Individual. Well, okay. Probably the only thing I can think of is the sort of thing that Greta Thunberg did, which is she went to the Parliament and kept on going, and then other people joined in. And so, in a sense, you have to get people behind you to get behavioural change. And it's quite a difficult thing to do. But when I noticed Dave Attenborough combining with Greta Thunberg, that seemed to be very powerful. So you have to, I'd call it, lead with integrity. In other words, make changes, but be, in other words, practice what you preach and show leadership. That is how you might start getting systemic change, because it needs to get embedded in policy and policy action. It's quite difficult.
I might add a comment that the questioner here, Rachel Bolstad herself, is very active in the field of education in climate change, which I think is enormously important.
Yes, well, that's very good, because the number of young people that realise what is happening, and that's probably, I don't know, I'm not aware of when primary school teachers, for example, started teaching about climate change and global warming, but that is a very important level, because I've noticed that when people get motivated and activated, it seems to be from the age of 12 that happens. And so education is incredibly important.
Over to you, Chris.
Right, a question about EVs, electric vehicles.
Yes.
So on the one hand, we've got a sort of an efficient sort of low carbon transport possibility there with EVs, but there's issues around batteries, right? The rare earths and minerals and the carbon footprint of extracting those, mining those, and then the question of battery life and how it runs down relatively quickly. And so overall, if you could compare those with a petrol car, are you really better off buying an EV or stick to your old petrol car? That's the question.
Yes, you are, because a petrol car directly puts carbon dioxide into the atmosphere. Sure, in the manufacturing process, there'll be some carbon footprint, but overall, if you look at the lifetime and what petrol cars produce, you're much better at using an EV. And if you look at what's happening overseas, there's a huge push for EVs, but better still is active transport yourself, which is cycling and walking and having neighborhoods that you don't have to travel huge distances. So the day of, I would say, the combustion engine is probably limited, because they're based on use of fossil fuels.
Right. Thanks. Yeah, and I completely agree about the whole active travel, active transport thing. That's because
Mm.
I think for many of these things, it's not just a question of carbon emissions, but also there's benefits for the cost of living perspective and also
Yep.
for your own health. So
Yep. Lots
there's
of health benefits.
yeah. So it's not just a carbon benefit. Yeah.
Yes.
Joanna, over to you.
Yeah. Annette Litherland asks about the very steeply rising methane levels in the atmosphere, and if we understand where those are coming from.
Oh, well, Martin Manning is the expert in New Zealand on this. He says, no, they haven't measured methane that long in the atmosphere. So they're only starting to understand the methane pathways. And there are surprises coming along because methane stabilized, but suddenly it's rapidly increasing. And the one thought is it could be that the climate system is adjusting to higher methane levels, and they seem to have detected a similar thing happening at one glacial interglacial boundary, but they feel much more work needs to be done in that area. But it's an important point. It's rapidly rising at the moment, and some of it is from ruminant agriculture. Some of it might be from wetlands. There's not enough known about methane chemistry or atmospheric chemistry. So watch the space.
Thank you. Your turn, Chris.
Right, I'm going right down to the bottom now. There's another question from Lindsay Wood. Can you please comment on the fact that IPCC emissions reduction targets are based only on a better than 50% probability of keeping within 1.5 or 2 degrees?
Say that again.
The targets in the IPCC emissions, their reduction targets, e.g. AR6, SYR, are based only on a better than 50% probability. So, there's still an awful lot of uncertainty around all of this, isn't there?
There is, but it looks like that the 1.5 degrees is probably going to be reached in the next decade. So it appears that the chances of keeping below that are very low. That's how I'd answer that one.
Do you think they'll become, as time goes by, the degree of uncertainty, the probability will increase of
the certainty, you mean?
The certainty, yeah.
Yes, well, science keeps on investigating, so it will narrow it down, but there's always some uncertainty. But we know the trajectory.
Mm-hmm.
Unless we reduce our emissions, we're going to keep warming.
Okay. Carol Briesman asks about the impact on global atmospheric readings with the increase of large bushfires. And she comments that living on the Kapiti Coast, they had haze from the Australian bushfires a few years ago.
Well, what you're doing is obviously as soon as you burn vegetation, you're combining oxygen with the carbon in the wood, and that's going as carbon dioxide. Wars must produce a lot of carbon dioxide as well, as you look at the smoke and fires and everything. So yes, they definitely would. The wildfires would, you're turning what is wood and burning it and ending up with carbon dioxide. So yes, it does. Wildfires certainly do increase that, and the risk of wildfires gets higher as temperatures increase.
Okay, and a question from Timo Neubauer. Can you give us an indication of what our current climate trajectory actually means for us here in Nelson?
Okay, so what it means, well, so every time the temperature goes up by a degree, you're holding more moisture in the atmosphere, about 4% more. And so when you do get heavy rainfall events, there will certainly be more severe floods. And we've been seeing this, the Auckland anniversary weekend floods and Cyclone Gabrielle, that the atmospheric loading of moisture gets higher, and therefore when it does rain, you get more intense rainstorms. And of course, Nelson is exposed to the north, and so can get flooding rainfalls. I'm not sure about areas around Nelson, Tasman Bay and Golden Bay, whether the area is threatened by sea level rise. I don't have the local knowledge to talk about that, but there'd be, hopefully there's been surveys done by the regional council and the local territorial local authorities on which areas might be affected by flooding. And that's either sea level rise inundation or river flooding. So what comes down the rivers, those seem to be the greatest, shall we say, impacts. There's also lots of other impacts. If it gets warmer, you get more pests and diseases, etc., etc.
Thanks. Joanna?
From Neville Smith. Even if New Zealand emits no further greenhouse gases, we'll still be affected by climate change because it's a global, not local effect. Could you please comment on the adequacy of proposed mitigation practices in New Zealand?
Sure. Our contributions are small, but I think when it's the Gandhi principle, what you will do will be insignificant, but it's significant that you do it. It's, if you add up global populations, we all have to buy into this. It's not just, oh, well, our contribution is very small. And I answer this by saying, well, if I stop paying taxes, it would have no effect on the government's tax take. But it's something that morally we all have to contribute to, and not just say, oh, well, the effect will be insignificant. Sure, it will be, but it's important that we all do it because we're showing a bit of leadership and moral responsibility there. And I'm sure if you asked your grandchildren about that, I think they'd have definite views.
Chris, do you want to ask the last question?
You have one more. Okay. From Fiona Eade, does today's strategy released by the government take us forward? And I must admit, I haven't had time to look at that yet. But if it's not possible to answer, just
no, well, I don't know what it was. I know I hadn't caught up with it. There was a strategy release.
I'll give you a little clue. There's considerable emphasis on carbon capture and sequestration.
Well, okay. If it's carbon capture and storage, that comes into the realm of what I'd call a technological fix. Carbon capture and storage is not a proven technology. No one's yet been able to demonstrate it works, if that's what it was about, that would be my view. There's a lot of, shall we say, oh, technology will fix it, but no, we have to do the hard yards ourselves. And this involves, we can do it, but involves us collectively saving energy and the things I've mentioned in my talk.
That was a good one to end on, Jim. It involves all of us doing the hard slog of
Yep.
reducing emissions. That's a good
Indeed.
place to draw this to a conclusion. And thank you very much, Jim. I want to mention in a recent interview, someone asked Jim Salinger, what in life brings you most joy? And Jim's answer at that time was communicating climate science to all, and especially assisting the youth of today in understanding the science and getting them engaged in the issues. And it's also very pleasurable working with my climate science friends as it's a small and very cooperative community where we share ideas. And I think your dedication to communicating climate science has been much in evidence in the talk that you have given to us. And we're very pleased to have the privilege of hosting you, Jim. So thank you very much for being with us. And I'll mention to our audience that a recording of this presentation will be available on the Nelson Tasman Climate Forum website. And you will receive notice of that by email, together with an invitation to register for our newsletter if you wish. And I will now end with a closing karakia. Ko te hā, ko te rā, ko Tangaroa, ko te mana, ko te kotahitanga o ngā mātāwaka. Haumi e, hui e, taiki e. So we're united in paddling our waka and ready to pursue together our common purpose. Thank you, Jim. Thank you, audience. Thank you, Chris. And thank you to Marlene and Christina, who in the background handle the tech part of this. Thanks to all. Good night.
And thank you, me, for the opportunity.
You're welcome.